So we talked a little bit in class about the normal model, like drawing it and the 68, 95, 99.7 rule. But let's go a little more in depth about what exactly that means. A normal model is unimodal and symmetric. It has a very specific shape, not just symmetric and unimodal, but it's this exact shape here, often called a bell-shaped curve, although I've never seen a bell that looks like that, so who knows. But we study the normal model because a lot of things are approximated very well with normal models. In fact, there's some pretty powerful statistics you can do. That's the kind of thing people do in research. But we don't get into that until stats 2. So this is the stats 1 version. We tend to keep it pretty simple. So a variable may be approximated with a normal model if it has to be a quantitative variable. So, numbers have to be there, preferably decimal numbers, but we can approximate it without. It's just not quite as good an approximation. The distribution has to be unimodal, clearly, because the normal model is unimodal. But to approximate it only needs to be roughly symmetric. It doesn't need to be perfectly symmetric to be a decent approximation. Really importantly is also we should have a reason to believe that the variable should follow a normal model, not just because the data says so. So just to talk about that, I took some images on the internet with Google Images search. I'm crediting them here, so hopefully that's not illegal. But here is a weight distribution for adults. I don't know where this data comes from, but you can see this is unimodal. There's one strong peak. It's not really symmetric. It seems to be skewed right because there's more data on the right. But also that's what you'd expect from a weight distribution. There's a lot of people around the same weight, but, there's an upper tail because, you could be 20 pounds overweight or 30 or 40 or 180. So that's just the whole distribution tends to be right skewed there. So you would never expect this to be normal, even if your data made it look like it was. Weights of animals, if they're on the same diet or very similar diet, like cows in a pasture or something, those could be approximated with a normal model if all the cows eat the same thing and have about the same activity level and stuff like that. Other things, though, like here's another one, a height distribution. So here they've played into some gender roles by color coding pink and blue, which I thought we were getting over that, but maybe this is an older image from the 90s or something. But if you just look at the bars here for the women's heights in particular, is it unimodal? Yes, there's one of these bars is really high, but there is a strong peak. Is it roughly symmetric? Yeah, roughly. It's not perfectly symmetric, so we can model that with a normal model. Why is this one bar so high? I don't know. Maybe that's just what we call sampling variability. We just happen to get more women of that height in this sample. We can't see the data as well for the men here, so we don't know for sure if it's symmetric, but whoever put this together made a blue bar fit, and it certainly seems to fit pretty well on this side, although it does have more of a spread. I'm a little cautious about seeing the rest of it if this fits very well, but heights are often approximated well with a normal model, assuming you're talking about, the same population again. Let's look at some of our class data, which is a little trickier. Now, in the class data that I had you all do, we didn't have that many data points. We got 18, including me. And some people didn't feel like giving certain information, or maybe they didn't get through it, which is totally fine. But let's just look at some of these. So if we do a distribution of the color perception test, this isn't really unimodal. You can see the bars are kind of all up and down. There's not much we can do with this. Is it roughly symmetric? No. Now, what if we had a lot more data? Maybe instead of 18 observations, what if we had several thousand? Would we expect to see a unimodal distribution? If we had several thousand, I think we probably would, because most people would be at some common scores. But we don't know for sure. Maybe, everything from 5 to 10 is equally likely. But we're also assuming that everyone has the same screen and the same testing conditions, same light here. The distorted tunes distribution was not even close. It's incredibly left skewed. There were a number of people who are really good in this class about identifying these tunes. I scored, well, I'm not going to tell you, but it was definitely at this end. So this is definitely not approximated by a normal distribution. On the quick IQ test, this looks approximately normal because it's unimodal, it's roughly symmetric. Problem is we still have a small sample size, but IQ tests, along with a lot of other tests, are designed to be a normal model in that it's very difficult to get all of them right, And there aren't many people who would get none of them right, assuming they were taking the test legitimately and not just guessing or making up answers or something. So IQ tests should be normally distributed, but that would be with a real IQ test designed by a professional that was free of bias in, some laboratory conditions. So age distribution, clearly heavily right skewed. It's unimodal, but we wouldn't expect the ages of people in a community college class to be symmetric. There's a lot of the younger folks, as I call them, and then it skews up to people closer to my age up here. Heights, we get a pretty good distribution here, good in terms of like close to normal. The previous one we looked at for height split male and female out separately, but realistically in a diverse population, the split is not as big as it seems like. So here you might be able to approximate this with a normal, but height is kind of a weird thing. I know people in like Amsterdam, for instance, are very tall. So if you were doing this with people from different regions or something, it might get a little more complicated, but it works pretty well for our class at least. Arm span distribution, well, we kind of have what looks to be a bit of a bimodal distribution here. We got a peak here and a smaller peak here. I think that's just because when we do this in class, we usually measure our arm spans. I think maybe some people here measured their arm length instead of like their fingertip to fingertip length. But that's another one that should work pretty well if your population is pretty similar. Hand span distribution looks pretty right skewed. But we just don't have very much data, and so many people were at either 3 or 3.5 inches that it's kind of hard to tell if that would be like right skewed if we had more data or not. In the next video, we will look at some theoretical cases and decide whether those should be approximately normal or not.